Hi. So we're going to look at cables and plugs today. So a couple of lessons ago, we looked at alternating current. That's how electricity comes into your house. How does it get around your house? How is it transmitted? It's transmitted through a plug along a cable. Some of these cables are in the wall. Some of these cables go along the floor. And we're going to look about how these are made to keep you safe. And we're going to look at how they're set up in your house. But let's just kind of get our brain working first. Can you list 5 devices in your house that you have to plug in to operate, as in they will only work when they're plugged in? Can you give me another 4, that will run on batteries, just batteries? They don't need to be plugged in at all. 3 that will plug in to charge and then can be used unplugged. And 2 things in your house that will have a transformer. Okay, pause the video, write down the answers. Okay, so 5 devices in your house that you have to plug in to operate. So big things, big devices: your washing machine, your fridge, freezer, your tumble dryer, toaster, kettle. All of those things you have to have plugged in to work. They will not work. They won't run on a battery. Things that run on batteries only. Calculator runs on batteries. Only runs on batteries. I've got other things run on batteries. I've got a small laser that I use that the cat chases around. That runs on batteries only. My daughter has lots of fairy lights in her bedroom. They run on batteries. That's 3. What else runs on batteries? I have a fan next to my bed when it's hot in the summer. That runs on batteries. 3 devices that charge from a plug but then run on batteries. My laptop runs on a battery. It's charging right now, but if I unplugged it, it would carry on working. Mobile phones will do the same. And I've got a little mini speaker that plugs in. That will charge up, and then once it's charged, I can carry it around. Things in your house that will have a transformer. Transformers are, if you remember from the previous lesson, things that step up or step down, change the amount of voltage and current that goes into a different amount of voltage and current. For example, if it has a big block somewhere on the wire, my laptop has a big block on the wire, that means it's a transformer. And my electric toothbrush charges via a transformer. The actual bit that it sits on is a type of transformer. Good. Okay, so first things first, we'll talk about electrical safety. Inside these plugs, there is a fuse. I'm going to open this one in a moment. The fuses are kind of one of the first or main lines of defense in your house to stop you from getting electrocuted. Basically, they're like a rope bridge, for the electric current. If the rope bridge has too many people walking across the rope bridge, it will snap, and everyone on it will fall into the ravine and get eaten by crocodiles and die. No, if the bridge has too many people on the bridge, it breaks. No more can pass. And it's the same thing for the wire inside a fuse. You normally see the fuse looking like this here, which is the one on the left. So it's got the metal ends and it's ceramic. So it's made of kind of like the same material sink or toilet is made from, but obviously thinner. You can't see the fuse inside. The one on the right, you can actually see what the wire would actually look like. And all that is when the current goes through, if the current gets too high, that fuse melts. And if it melts, the current can no longer pass. In fact, there are different types of fuses. So the one I think in that picture is a 13 amp fuse. And that's the highest you will have in your house, a 13 amp fuse. That's normally things that are big or things that do heating. So a washing machine is big and it does heating. It heats up the water before washing your clothes. A kettle produces a lot of heat very fast. A hairdryer or hair strainers, if they heat, they normally draw a lot of current. If they draw a lot of current, they'll need to have a 13 amp fuse, because if they have a lower fuse, then every time they turn on, they'll just blow. For example, like a kettle will probably operate at about 11 amps. So if you put a 5 amp fuse in a kettle, every time you turn the kettle on, the fuse would blow and you'd have to replace the fuse. Pointless. So you have to make sure you have the right fuse. General rule, if it doesn't have any real moving parts, like a lamp, you might use a 3 amp fuse. If it has something that moves, so thing with a motor, like a games console, a PlayStation, the disc spins round, a DVD player, a Blu-ray player. So if something's moving, then there's a good chance it'll be a 5 amp, and if it heats a washing machine, therefore you'll use a 13 amp. Let's have a look inside. Right, I'm going to see if and let's see if I can make this. Where is this? Boink. Oh no, that wasn't meant to happen. Okay, plug. Right, let me invert because it's the wrong way around. Check. There we go. Right, the lighting isn't brilliant, so unfortunately that's quite bright. But you can see your plug. It's a 3-pin plug. In the UK, we have 3-pin plugs. They're brilliantly, smartly designed. They've got this one here at the front. This is the earth pin. It's slightly longer than the other two, and often you'll see. And this is an extension lead, so I can show you. Inside this one here, there's a little switch, a little kind of lever. And inside these two, there's a little doorway, like a little barrier. And these two won't go in. You can't get these 2 pins in unless you've got this pin in. So it will work. So this goes in. So you can see, there we go. This goes in first, the longer one. And then once we get to a certain point, you can actually hear the thing open, and so the plug can go in. And you notice also these pins here have got like a black plastic coating, which means if you accidentally manage to, my fat fingers won't, if I manage to get my fingers in here, they're not a conductor. Like the metal bits there are conductors, but by the time they're in, touching the other conductors, you can't get your fingers in and touch them, or if you can, it's only the black plastic. So the plug is designed very cleverly to stop you getting a shock when you put it in or to pull it out. There are 3 screws. There's one here in the middle, and that holds the back plate on. And these 2 here, which hold, it says here, cord grip, it holds this wire in place. If I open it, you don't actually have to take this screw all the way out. You can just do it. And you can see that this back has just come off. Just drop the screwdriver. And inside we have 3 wires. We have, this is mirrored, the camera, so it's reversed. So actually, normally if you open it, it'll look different. But you've got the fuse here, and the fuse is connected to the brown wire. The brown wire is the live wire. That's why it has to be connected to the fuse. And so what happens is the electric current comes in here, along this pin, then it goes through the fuse, and then through this connector, and then inside, let me poke this out. It's quite snug, but here we have, so it's connected, the wire is connected, there's a little bit of copper sticking out the end of the wire, and there's a screw here, so this is screwed into place, and that wire, so the current comes along here, along the fuse, and then down this wire. Put this back in. Okay, and then the electric current goes along this wire into your device, does whatever it needs to do, and then on its way back out, it comes along and goes through the blue, which is the neutral wire, back into this pin, and out, back through to the mains. And so that's how the electric current goes in and out in a complete loop. But there is a 3rd pin, an additional pin, which doesn't provide any useful energy to the circuit. It's not it's not part of the current and voltage. But what it is another one of the clever safety devices that we have in our plugs. If your device has a metal case, metal's a conductor, and now if somehow moving things around or something got damaged, one of these wires, like later on, a wire from this part down here came loose and touched the metal, that whole metal case would be electrified. And so if you touched it, you'd get an electric shock. This earth wire is connected to the outside of that metal cage. So your washing machine, your fridge, those things, they'll have an earth wire. So if you something does go wrong and a wire does come loose, and you touch the door, you won't get electrocuted because that extra electricity just flows down this earth wire, down in this pin, which goes into this pin, which goes out, down into the earth underneath your house, making you all safe. These wires are all coated in plastic, obviously, so you can't touch. And also then the wire itself is coated in plastic again, and it's held in place with these two screws to make sure that if you do somehow manage to pull it, you're not going to pull the wires out, exposing anything, being dangerous. So the plug is pretty well designed to keep you safe. Right, let's see if I can go back to... Woohoo! There I am. See if I can move it without it going horribly wrong. Right, so, and... now I'm upside down. Woohoo! There we go. Excellent. So this is your plug. Like I said, you look slightly different from how it was before because my camera would have made it reversed, so it looked the opposite. But that's how it would look if you opened it. In fact, it's probably a good thing for you to draw. So pause the video and sketch this for me right now. Or no, actually don't. Just find a picture online and stick it in. You can do that. But just note it, okay? Live wire, brown. Neutral wire, blue. Earth wire, green and yellow. And so inside your house, you have these loops. And actually, I'm going to jump on ahead. You should recognize, hopefully, this. You'll have one of these somewhere in your house, depending on how big you are, how big your house is. You might have more or less of these little switches. And basically, this is, so like on one floor, if you've got more than one floor in your house, all the, say, plug sockets might be on one loop. And so actually, if one of them blows, if like something goes wrong with this and it fuses, all of the plug sockets will fuse. But basically, what happens is the live wire, the electric current comes in and it travels around all of the plug sockets. So like this, and then it travels out via the blue neutral wire. The earth wire is just the security, the safety feature. Another really good safety feature you have, so you've got the fuse, which is going to go if too high current. You've got the earth wire in case something goes wrong. But you've also got fuse boxes. These actually, the fuse box, these little individual switches are called RCDs, called residual current devices, which basically work like a kind of electromagnet. And so what happens is normally, there's lots of stuff on this diagram, so don't panic. Let me see if I can get the pen to work. It's not working lately. Normally, yeah, it's working. Normally the current goes in and goes along. It also, some of it goes down here, making this electromagnet, or it can go along this way. Now, what happens is, if the current gets too big, bigger than it should be, what happens is more current will flow through this electromagnet. And what happens when you increase the current on an electromagnet? It becomes stronger, becomes more magnetic. And we can see, so this is like normal functioning at the top diagram. The current's going through, but the magnet's not strong enough to do anything. The diagram at the bottom shows the current coming through and it's too big. So what happens is, when it's too big, the magnet becomes stronger and it pulls that bit of metal down. And that breaks the circuit. And that's what happens when you have the fuse goes in your house. You may have plugged too many things in at once. You've turned on the toaster, the kettle, the hairdryer, the hair straighteners, the hair curlers, and all the other hair devices in your house, and that's drawn too much current. And then, so what happens is, there's a lot of current in this, so that becomes very magnetic, pulls down the catch here, this switch contact, cut all the electricity for that section. And what you have to do is you have to go back and flick the switch. But the important thing is, why did that happen? If you just go back and flick the switch and you haven't changed what's happening, that'll happen again. So for example, if you do turn 7 things on very quickly, it might draw out too much current. Before you switch, make sure you turn all those things off. Otherwise, the same thing will happen again. So you've got loads of safety devices in your house. If you manage to electrocute yourself at home, you're really going some, or maybe the house just is not cleverly wired. So we've got, just to review, your electricity comes into your house and you access it by plugging things in. There are different loops of how the electricity flows around your house, hopefully arranged by a qualified electrician. And inside this plug, the electric current comes in to the live wire via a fuse to keep you safe. If the current's too big, the fuse breaks the circuit, everyone's safe. Down the live wire, back up, out the neutral wire. The earth wire is only there as an extra layer of protection in case a wire comes loose and there's a chance you could get an electric shock. You also, on top of that, have these circuit breaker, this RCD in your fuse box, where if the current gets too big, it turns the whole electrical source off. Wow, loads of information there. There we go. So there were just a series of questions. Name the color of each of the wires in a main plug. Explain why sockets are wired in parallel. Explain why brass and alloy of copper and zinc is better than copper for pins of a 3-pin plug. Oh, you have to do a bit of research. Give a reason why cables that are worn away or damaged are dangerous. Match the list of parts in a 3-pin plug. Explain why each of the 3 wires is insulated. Describe how the metal case of an electrical appliance is connected to the earth. Explain why the cables joining the wall sockets in the house need to be thicker than the cables joining the light fittings. Describe the difference between a 2-core cable and a 3-core cable. Think about whether it's made from metal or not. And determine what appliances should be having a 2 or a 3-core cable. You might have to do a little bit of research for that extra one. Go on. So answer the questions. Just write down the answers and send them to your teacher. Good luck. Love you. Bye.